because I would have received an email or some message from people and going like, "Hey, you didn't change the due date. I was trying to turn it in."
I worked on it. Worked on it.
Yeah. Well, it's a really low point value thing, right? I think it's only 4 points, and that's 4 points over all of the points that you get with all of the labs, right? So in terms of point value, it's not that much. But in terms of how you prepare for your final exam, I think it's really useful. So just being able to put time into the whole thing, give it a try, as far as you can go, that's really helpful because you can probably ask questions in today's lecture related to the assignment and also related to all the concepts that we have talked about so far because you have tried it. Okay, for people who did not even bother to try it, they wouldn't be able to. I do apologize because my ring is just going crazy because somebody is probably working on my front yard. All right. So let me go to the, I think I put everything into the announcement. So let me go back to the announcement and retrieve the zip file, and then we'll start from there. Okay. So it's the zip file. I'll put it into my temp folder. It's all good. All right. So unzip node-1.zip, and we want to replace all. Okay, sure. There we go. All right, so now we have node.c, node.ttpasm. All right, so how do you guys want me to go over this? Do you want me to just go straight into the implementation of Traverse, or do you want me to talk about the concept a little bit first?
Traverse.
Okay, we got one for Traverse. Is that okay? So I can, if the discussion of Traverse prompts some of the questions, I can always go back and explain the concepts. Okay. All right. So let's take a look at Traverse in C code first, and then we'll go ahead and try to implement that in assembly code. So this is Traverse. It has a void return type, which means we don't have to put anything special in register A at the end of Traverse because it has no specific value to return. It has two parameters. The first parameter is PTR or pointer. It is a pointer to a struct node, which means if you look at the value of PTR, it is the address of a struct node. The second parameter is a little bit more cryptic because it is called array. It is a pointer to an unsigned 8-bit integer. Okay. So later on, I'm going to use a diagram to show you what is a pointer to a pointer. Okay, so that's going to happen after I create the code, and then I will go ahead and okay, let me. Okay, this should all be off now. Okay, there we go. So once I run this code in, once I have the runtime data in the analysis tab, that's when I can draw a picture of what is happening on the stack. All right, so we'll go into the subroutine. We'll go ahead and actually implement the subroutine at this point. So what I have here is just the return code. So what I need to do now is to kind of add the content corresponding to line 11 to line 16 of the function. But before I do that, I want to know what the stack is going to look like. So we know we have a second parameter called array. We have a first parameter that we call PTR, and then we have the return address. The function does not have any local variables, so this is all we need on the stack. In other words, as long as the stack pointer ends up pointing here, we're good. Is that okay so far? Okay. But in general, we want to kind of think about, well, what if we have local variables? So in this case, I'm going to define traverse. I'm just going to use T instead of using traverse because it's a lot of typing. So T underscore something is just the abbreviation of traverse underscore something. So T underscore LVS local variable size is 0 because we do not have any local variables. And then we have T underscore PTR. which is T underscore LVS 1 plus. So this one here is basically counting the return address so that we provide that one extra byte between the end of all the local variables and the first parameter. Is that okay? Because if we do have local variables, LVS would have been some non-zero integer. And that's going to indicate the number of bytes that we need to reserve for local variables. In this case, it's 0. So T underscore PTR is trying to tell me where can I find PTR relative to where the stack pointer is pointing to. So the stack pointer is pointing to the first local variable, if I had any, and then LVS is going to say that's the size, that's the number of bytes that we need to reserve for local variables. So this one, this extra one is basically saying, oh wait, there's one extra byte that we need to account for from where the stack pointer points to, and that turns out to be the return address. Is that okay? Does everybody understand why there is a 1 plus in order to calculate the displacement or offset to the first parameter of a function?
Can you draw it on the board? Just like
Yeah. I think when we run this and we look at the trace, that's when I would draw a picture because that actually would give me the solid concrete values, and then I can actually draw the pointers around. So just wait a little bit until we get to that point. And today I don't have any structured lab activity, so we can go over the lecture time a little bit into the lab time if we need to. So we have T underscore array. That's going to be T underscore PTR 1 plus. So I have now calculated all the offset to various items in the call frame that I need. And then what we need to do next is to do the allocation. So we have LDIA with T underscore LVS, which turns out to be 0 anyways, but I still want to have this code here just in case later on I decide, I do want to have a local variable, a bunch of local variables, then all I need to do is to change the label definition, but the code is already accounted for in terms of allocating and deallocating for the local variables. So at this point, because I really do not have any local variables, line 18, 19 doesn't do a single thing because LVS is actually 0. And the same thing can be said about line 23 and line 24 because T underscore LVS is actually 0. So subtracting 0 from D and adding 0 to D doesn't do anything useful. Okay. All right, so now we are on line 11. We can now say, okay, we got everything allocated. How do I check whether pointer is non-zero or not? Because when we see this kind of construct in C, it really is trying to cast a scalar value into a Boolean. And the way we do that is to equate 0 to false. Anything that is not 0 is true. Is that okay? All right. But before we do any checking and any testing, we need to get to PTR first, right? So that's what we need to do with the LDIA T underscore PTR. That's going to be the offset. So once again, the comment here, I can say A is now the address of PTR minus the value of the stack pointer. Because it is a displacement, it is the number of bytes between where I can find PTR on the stack from where the stack pointer is pointing to. Is that okay? Does everybody understand why I chose to represent what is in register A using that expression?
What's the address? It's the address.
No, it is not the address. It is the offset. It is the number of bytes between where the stack pointer points to and where I can find parameter PTR. All right. So when I run this code, it will be more clear of what is on the stack and where the stack pointer is pointing to. And then the next instruction is add AD. So technically speaking, this is basically what it used to have, and then we add d back to it. So using even just algebra, you know that we are now left with the address of PTR in register A. And we are not really checking whether the address of PTR is 0 or not. We're trying to get to the value of PTR. So that means we need one LDAA instruction here. So this is basically saying A is now the dereference of the address of PTR, and the referencing and the address of, they cancel out each other. So we end up with just the value of PTR. So we're still doing okay so far because these three lines, okay, line 21, 22, and 23, are super duper important because they are based on, okay, how the call frame is structured. Where do we find parameters? Where do we find the return address? Where do we find the local variable? So it depends on that concept. Two, it depends on the concept of this, the number of bytes between certain things and where the stack pointer points to. And that's why we need to add the stack pointer back to the displacement. And then the third thing is also important is what we have done so far in line 22 is get to the address of something that is in the frame. But if you need to access the value of that thing, you need a dereference, which is the only way you can do dereference in TTP is either the ST or the LD instruction. Okay, the extra parentheses around register A on line 23 is indicating that is where the dereferencing happens. But that's just syntactical eye candy. Okay, the parentheses are really just eye candy. I insisted to use this syntax so that I can remember which one is being dereferenced. But in return, what we are really doing, if you look at the architecture, is register A is connected to the A port of RAM, but we are also connecting the D port of RAM back to register A. So register A controls which location in RAM I want to examine, but it is also getting updated by the content at the same location. Are we still doing okay so far? Okay. All right, so now that we have the value of PTR, I can now check whether it's 0 or not. You can compare that to 0, but that takes extra instructions. The quicker way to do it is to use the AND AA instruction. So the AND AA instruction is not destructive to register A, but it does push the register A through the ALU. So in this sense, this push has nothing to do with the stack. All it says is to say, okay, we are presenting the value of A through the ALU, and the idea is we want to use the value of A to change the flags, the Z flag and also the S flag, the sign flag. The sign flag is useless in this particular program, but the Z flag is useful because the Z flag will be set if and only if A is 0 to begin with. So that means right after this, we can do a JCI instruction. So the JCI instruction is basically saying, okay, I will branch to whatever you specify if and only if the Z flag is a 1. So in this context, it's basically saying, I will go to the location where you indicate the label if and only if register A, which is PTR, is 0. So if you look at the C code, if PTR is 0, do I have anything to do in the conditional statement? If you look at the structure of the conditional statement here, if PTR is 0, if it's a null pointer, do I have anything to do? Nope, there's no else branch, right? So we can go straight to the end of the conditional statement. So I'm just going to say T underscore and if 1 is the end of that conditional statement. And the way I write this code is I typically will also define the label right away and also comment and say this is the end of the if statement. So now, if I continue execution and not take the branch, it means your PTR is not null. So I really like to leave comments to myself, because otherwise, after a while, I would also forget what does it mean to be on line 28 again. So this is a reminder to myself that if I continue execution on line 28, it means that, well, we know PTR is non-null. It is not a 0. So are we still doing okay so far with this? questions? All right. All right. So inside the then branch, because we are basically in the then branch now, and there's no need to go around the else branch because there's no else branch to begin with. So I'm done with the control structure of the conditional state. So now what we are left to do is to call traverse recursively and do this really awkward thing on line 14, which is probably the hardest thing to implement of this entire program. And then we do line 15, which is kind of like line 13, except instead of using the L member, we're using the R member. And so we'll go ahead and do that. So right now I'm on line 13 of the C code. Before we call a subroutine, we have to push all the parameters, push all the arguments. So the first argument is array. Well, that's an easy one, right? So you just say LDI A with T underscore array. That's the offset in number of bytes from where the stack pointer points to array as a parameter. And then you add AD, that becomes the address of array as a parameter. That's not what I want because I want to push the value of array. So that means I need an LDAA. So now register A has the value of array as a parameter. Now I can push it. Decrement D, STDA. So now we have pushed array on the stack. This is my second argument. So now we are ready to push the first argument. So let me just kind of pause here and make sure this is looking okay for you guys. Do we have any questions about pushing array on the stack as the second argument? So we all good? Okay, so now we need to implement the pushing of the first argument, which is the member L of the structure that is pointed to by PTR as a parameter. Is that okay? All right. So it is really crucial that we first understand the C concept and be able to describe what we are really trying to push on the stack. It is member L of the structure that is pointed to by PTR. So that means the first thing I need to access is PTR. Okay, I can't do the rest unless I know what PTR is. So the code is similar. Okay, load A with T underscore PTR. Add AD, that would become the address of PTR, LDAA, that would be PTR, the value of PTR. Now, we have a problem here, okay? But I'm not gonna fix it, okay? I will actually let this program not do the correct thing because I want to illustrate what happens when we have that particular problem. So instead of just explaining what the problem is and then give you the fix right away, which is deceptively simple, okay? Because most people just go like, okay, we get it, okay? We need a 1 plus here. So instead of doing that, I want to show you what happens when we do not fix this problem, because that might actually give you a better explanation and also a more visual result to show you, oh, so that's what happens when we do not have a 1 plus here. Okay, so I'm just going to leave behind a little remark here and say there's a to do, okay, 1 plus, because I want you to also keep an eye out on line 34 when we run the code and go like, okay, we know this line is wrong, but why is it wrong? What is showing on the screen in the analysis tab that is telling me that this is not right? Okay. But we'll just pretend that it is right as it is and continue. So right now, register A is PTR. PTR itself, according to the C code type, is a pointer to a struct node, which means what is in register A now is the address of a struct node. What we want to push is not the entire struct node. We just want to push member L on the stack. Okay. But we also know where to find member L because that's why we define all those labels. So we put that particular value, node underscore L, into register B, and then we add register B to register A. So at this point, register A becomes the address of member L of the structure that PTR is pointing to, not counting the problem corresponding to the to-dos. Yeah, I mean, at this point, it is all good. Okay. But we don't want to push the address of member L on the stack. We want to push the value of member L. So that means we need one more LDAA, like so. And now we should have member L calculated, and then we just have to push it on the stack. Decrement the stack pointer, stda, and we have now both of the arguments on the stack. And then what we'll do next is to push the return address. LDI, I mean, there are a few ways to do it, but this is the usual way that we do it. So dot 5 plus stda jmpi to the same subroutine, which is traverse. And when we come back, we have to increment d twice to deallocate the two arguments, because the subroutine or the subroutine that we're calling is only going to deallocate or pop the return address. Besides the return address, we have the two arguments. They're still sitting on the stack, doing absolutely nothing by this time because the function call is over. Why do I still want to keep those two arguments on the stack? I don't. So we have to use to increment d to deallocate it. And that should conclude line 13 of this entire program. All right? And that's all I'm going to do, because I'm not going to implement any further unless I know this line is doing what it is supposed to be doing. Because otherwise, I would just be replicating wrong code all over the place, which means I have multiple places to fix the code. I think it's probably a better idea to debug it once, just to make sure that this part is working, which I know is not going to work because of the to-do thing. Are we good so far?
We didn't do the R yet.
Hmm?
Part, the R part yet.
Which part?
The R, the pointer, R variable.
R variable.
Does the node R, whatever it is, the third line 15.
Line 13.
15.
15.
That
oh, we are not going to do line 14 nor 15.
Okay.
I'm just because I want to test the code first.
Okay.
Because this particular program can be implemented in steps. So you can basically just go like, okay, I just want to do this part and see whether it works or not. All right. So now the question is, how do we know whether this code is working or not? So that's when you need to look at the C code and say, okay, what is the C code actually doing? So we go back to the C code, okay, and you can test the program with different things. So using N1 as a starting point is actually the hardest one, okay, because N1 has an L, okay. So if you look at how the structure is defined, okay. So if you look at how the structure is defined, L is the second member, R is the third member. So if you look at how N1 is defined, it has both a non-null L member and also a non-null R member. Okay, so that makes it kind of not easy to test. Okay, because so the easiest one to test is going to be N4 or N5. So to incrementally debug the program, I would change this to just N4. So if it is just N4, then according to the C code, okay, because if I just use N4, then PTR is just the address of N4, and it is not going to be null, and it will do one single recursive call because we are not implementing line 14 nor 15. So in the recursive call, it's going to use the L member of N4, which is a null here, to pass as PTR to the next invocation of traverse. So the next invocation of traverse will look at PTR, which is going to be null, and say, I got nothing to do. It's going to return, and then the first invocation of traverse would get back to here, and there's nothing after line 13 because I did not implement line 14 nor 15, so that would also just return. So it's not going to change anything, but we know that it should only go for two invocations of traverse before it decides, okay, it's time to go back. Are we still doing okay so far with this code? In terms of just analyzing what the C code should do, given that we changed the parameter from the address of N1 to the address of N4. Are we good so far? Now, the C code compiles, okay, which means you can actually just plug in the entire C code into online GDB and just run it step by step. Okay, step into, step into, step into, and you can then tell what is the behavior of the C code, and you will be looking for the same behavior in the assembly. Are we still doing okay so far?
I'm not really totally sure well, I'm not practicing anyways, but what the code's supposed to try and do.
What is code? You mean the C code?
C code, yeah.
Okay, so what the C code is trying to do, okay, let me see if I can find a better way to describe it. Okay, so using a picture would help. So let me see if I still have that clone up. Yep, it's still up, but it's not working anymore. So I'm gonna have to close it and start it again. So give me a second here to prep this. Okay, so there's that, and then I just need to get back to the original. All right. So the way it works in the C code, okay, still got one more script to run before this is all gonna work. All right, so it should work now. Yep. All right, so let me go to journal, add page after. There we go. Okay, so according to the C code, we have N1, and N1 has a particular value. Let me kind of switch between the windows so we can tell what is the value of N1. There we go. Nope, not that. We should be looking at, this the source code. There we go. So N1 has a value of 5. I'm just going to draw this thing in the other one, then I can show you what that is representing. So N1 also has a left referencing N2 and a right referencing N3, and then N2 has a value of 3. The left is a null value, and then the right is referencing N4. N4 has a value of 4. It has both left and right being null values. N3, on the other hand, has a value of 10. It has a left going to N5, a right that is going to a null. N5, on the other hand, has a value of 9, and it has null going to left and also going to right. Okay, so I got the picture already done, and let me go over the picture itself with you guys. Okay, so basically, this is what is happening. N1 as a structure has a left, which is a pointer to a struct node. It also has an R, which is the right hand side, which is also a pointer to a struct node. It has a value. The value is 5. So what you see here, this is basically representing L, left. This is representing R, which is right. So N1 points to N2 by its L member. So N2, on the other hand, has a value of 3. Its L value is a 0, so it's not pointing to anyone. But the R value, this is the L, this is the R. So the R value of N2 points to N4. N4 has a value of 4, but both the L and the R of N4 are pointing to null values. N1 has a R that is pointing to N3. N3 has a L that is pointing to N5. It has a value of 10 by itself. It also has an R that is null, which is not pointing to any particular struct node. N5, which is the last one that we need to talk about, has a value of 9, and it has a L of 0 and an R also of 0, so it doesn't have any descendants. So is that okay? Does everybody kind of understand how to look at this graph and see how it is correlating to how the structures are defined? You doing okay so far? All right. So what the program is doing, what Traverse is doing, is basically you're given a particular address to a node. So let's say we are given the address of M1. It first checks whether it is a null value or not. If it is a null, it doesn't do a single thing. Otherwise, it will say, okay, so let's look at the L branch here. Do the same thing over here for this entire subtree. Go back here, do something with this value of 5, and then do the traverse on the right-hand side of the entire tree too. That's basically what it's doing. So what it's doing with the value of the node itself is really just to append it to the end of the array that is pointed to by the pointer that is pointed to by array. Because array as a parameter is a double pointer, is a pointer to a pointer of an array of integers. So it would update that. I'm not sure whether I explained that correctly or not.
So there's
But
also
okay.
an array as well. There's the nodes, and there's also an array.
Well, we are not concerned about the array at this point. Okay, we're only concerned about how the nodes are structured. So if you were to give the address of N4 or N5 to Traverse, then it would look at the address of N4 and say, that's not 0. We got something to do. And then it would use the L member, which is a 0, to recursively call Traverse. So the second time Traverse is called, it will be passed a 0 as PTR, and the code, okay, so let me go back to the source code. So the code of Traverse would basically say, oh, PTR is null, I got nothing to do here, and that would stop the recursion. Are we doing okay so far with that? Okay. So now the question is, how do we test this code? Well, the way we test this code is to go to the main program here, and we have to change the parameter n1 to n4 because n4 is the one that's easier to debug. And I think we are ready to test run this code. So let me switch to another window here. I don't need that anymore. So we'll go ahead and use this. Submit node.ttp-asm. So this time it might actually time out, because I have that intentional flaw in the program, so it might actually time out. Actually, it does not even assemble correctly. Let's find out why it is not assembling correctly. So I need to look for the assembler. Oh, it's in the wrong tab. All right, so let me move the assembler tab back to what you guys can see. All right. So I'm looking for an assemble time error, which is reported here. T underscore end if one is not defined because I defined it only as end if without the one. So let me go back to the source code and fix that first. Yep. So see how the definition is just end if without the one. So that's the problem why we have an assemble time error. So I got it fixed. Let me try to submit again. Okay, object code is good. So this time the simulator may have to go for a little bit. It's done. And now we can go back to the analysis tab and try to figure out what it's doing. All right, so this time we're going to have to kind of take our time to figure out what is actually on the stack, okay, because that is important. So what we are doing is we are following the trace more or less line by line, but we don't have to do it really line by line until we get to the subroutine. And to do that, we can go back to the Assemble tab and then go to the entry point of Traverse and just say, I don't have to pay attention until we get into Traverse. So Traverse is starting at location 5. So that means I can go back to the analysis tab and go, until column A gets to 5, I really don't have much to worry about. So we're going to fast forward until column A is 5, which is right here. All right. So row 41 is representing when traverse is called the first time from main. But you can probably see that the tag, we've got a few things on the stack already. Because if you look at column C, we already got a bunch of stuff in it. So the question is, what is on the stack right now? So this is where it is important to understand what the main program itself is doing, or what the main function is doing. So to explain what is on the stack at this point, we have to go back to main, which is supplied to you, but nonetheless, you still have to understand it in order to figure out what is on the stack. So this is an important discussion of what is on the stack and what we use the stack for. So as far as main is concerned, it has two local variables. It has buffer and it has PTR. Buffer is the one that has a higher address, and the PTR is the one that has the lower address. So the way we associate these local variables with the labels is we use main PTR to be 0, which means right after I do all the allocation for local variables, the stack pointer should be pointing at PTR directly. Is that okay? And then on top of PTR would be buffer, and buffer has to do with buffer length, and buffer length is 8 in this case. Is that okay? That would be the first thing that we allocate. And I cannot remember whether this main is a regular function or not, because sometimes I do that. This one is not a regular function, so it doesn't have a return address. So right now, I need to draw a picture of what is on the stack. So let's go back to Zerno so we can actually see what picture we should be seeing, or what is on the stack. So what should be on the stack right now? Okay, if this is the stack, originally D is pointing to 1 byte past the end of the entire stack. This is the initialization. When D equals to 0, it is basically pointing to 1 byte past the end of the entire memory space. So what we're expecting now is to have buffer allocated first, and then PTR allocated secondly. So that means I'm looking for 1, 2, 3, 4, 5, 6, 7, 8 bytes here. So these 8 bytes are allocated for buffer. And then we have 1 extra byte here that is allocated for PTR. Okay? So let's do the counting backwards in hexadecimal, because that's what the trace is going to use. So we have location FF, FE, FD, FC, FB, FA, F9, F8. So these 8 locations are corresponding to buffer, with this location here being buffer bracket 0, and the last location here corresponding to buffer bracket 7. And then this is location F7. So we have everything from FF all the way down to F7 allocated only for local variables of main. Are we doing okay so far with this? This is what we expect the code to do. After the allocation, the stack pointer should be pointing here at location F7. Are we doing okay so far with this picture, or the concept that local variables are on the stack and then the subroutine itself is responsible for the allocation? Are we good? Okay. All right. So if that is the case, okay, if this is the picture or the map of how main is allocating its stuff, let's go back to the code again and figure out what main also needs to do. So we will look at the code in C first. So in C code, the first thing we do on line 32 is PTR is initialized to buffer. So that means PTR points to the first byte of buffer. Okay, because that C code in C, there's no way you can actually do an assignment of an array to another array. It doesn't work. So when you refer to an array, you're always referring to the address of the array. So PTR should point to the first byte of buffer. Okay, if that is the case, in the picture, what are we supposed to see? So in the picture here, what we're supposed to see is F7 should have a value of F8, and that's because F8 is the address of the first byte of buffer. So that's the first thing. This is the first memory write that we should expect to happen is location F7 would get a value of F8. Is that okay? So we want to check that first, okay? Because if main is not doing its thing correctly, I can probably just say, well, the subroutine won't be able to do anything correctly. So this is the first thing I need to check. So to do that, we have to go back to here, and then we just have to kind of look at the memory write and just keep going up until we find how F7 is changed. And this is it. So F7 is initialized, or the location at F7 is getting a value of F8. So we got that done correctly. Are we are we doing okay so far? This is just in main. This is not even in traverse. But I'm trying to give you a pictorial representation, what is supposed to be on the stack, and also giving you a method to check all of this stuff here using the analysis tab. Are we doing okay? All right. Now I understand that your homework assignment is already past due, and there's no that I mean, it's not going to be helpful to turn it in. But I think it will still be helpful if you can test your code and also run some of the sample programs that I have written in the past, or even when I'm done with this entire code, I would upload it so that you guys would have a copy. And when you run it, it would be helpful to look in the analysis tab and be able to explain what am I seeing here? Why am I putting this byte on the stack? What is it corresponding to? Is it a parameter? Is it a return address? Is it a local variable? Which line of the code am I, what line of code is it corresponding to? And so on. Okay, so all of those are important. So this will still continue to be a good tool to use for quote unquote studying for this class. All right, so let's switch back to the C code and see what next we have to do. On line 33, we have to make a call. This is the call from main to traverse. This is not a recursive call. This is from main. And we have to push the address of PTR on the stack first. Okay, so we are looking at the second argument of this call here. So now the question is, given the map that we saw earlier, well, let's not say earlier because I can always just kind of give you the map here. So given this map, okay, what am I supposed to be pushing? I'm pushing the address of PTR. So what should happen to the stack at this point? Go ahead. Oh, you just, all right.
You're calling what do you mean?
So the C code is, it's harder to show both the C code and the stack picture. Excuse me. We're talking about line 33, and we're trying to push the second argument right now. The second argument says we need to push the address of PTR. So remembering that that's what we need to do, this is the picture. Where is PTR in this picture? What is the address of PTR?
F7.
F7, very good. So we are supposed to push F7 on the stack. So how would I represent the pushing of the address of PTR on the stack?
You would have to first allocate the space, right?
Right? Okay, very good. So that means the first thing we do is we move the stack pointer, right? We move the stack pointer down by one location. All right, so we, let me see, do I stack delete? Nope. Nope, that's a, Okay, that's fine. I'm going to just use an eraser. Oh, I have. Interesting. I can delete stroke. There we go. Cool. So the first thing I do is I move the stack pointer down. So the stack pointer D is going to point to location F6 in this case. And then the second thing we do is to put something over there. So what should I put into location F6?
The second parameter or the second pointer.
Okay, so give me the hexadecimal value that should go to location F6.
F7.
F7. Okay, very good. Okay, so F6, location F6 should get the value of F7. This is what we're expecting because this is supposed to be the address of PTR, PTR being a local variable of main. Okay, is that okay? Because this is really kind of important to understand. Is that okay?
Yes.
But do you see how uh, the content at location F6 is a pointer to something in buffer? Do you see how F7 is the address of a pointer? That pointer, in return, points to, in this case, the first byte of buffer. And that's why it's a double asterisk, because it is a pointer to something in an array. Which also means if I want to, I can use a different color just so that it doesn't interfere with the rest. So this points here. This in return points here. So I'll be doing okay so far with the concept of a pointer to a pointer. All right. Okay. So now I can go ahead and oh, okay. I'm not going to erase it just yet, okay? Because let's go back to the C code and find out what we need to do next. So once we push PTR on the stack, the next thing we need to do is to push N4, the address of N4 on the stack. So where do we find N4? Well, this is where N4 is in C code. So in C code, N4 is a global variable, and global variables do not live on the stack. They just kind of live, quote unquote, among the object code, the instructions and stuff like that, depending on where you put those byte, instructions. So in the assembly code, so let me go back to the assembler. So if I go to the assemble tab, I can actually go find out exactly where is N4. Okay, I cannot remember where it's after or below. Probably right there. Okay, so N4 is right here, and it is at location 55. Is that okay? So if I go back to the map, okay, the next thing I'm going to push is the address. Oops, the address. Wrong color. Okay, Control Z to undo. Change the color back. This is supposed to be at the address of N4, but the address of N4, according to the assemble tab, is 55 in hexadecimal. So we go back to this one and we say, this location should get a value of 55 in hexadecimal, and that should be at location F5. Is that okay? So location F5 is the first argument, location F6 is the second argument, and then location F4 is going to be my return address. So let's go ahead and also designate location F4 to be the return address. The question is, what is supposed to be the return address? If you go to the assemble tab, well, we can actually find that out too. So we are in main, and we are just about to do the JMPI instruction. So the return address should be a 46. Because the return address, unless there are good reasons The return address is always going to be the address right after the JMPI when you call a subroutine. So in this case, the instruction right after the JMPI instruction is the highlighted cell, which is at location 46. So I'm going to go back to the map and update the map and say, okay, this is supposed to be 46 exactly. So are we still doing okay so far? Because at this point, I have not even taken a look at the actual trace in the analysis tab. I'm just looking at the source code to figure out what I should be seeing on the stack. Are we doing okay so far with this picture? Because unless you know what is supposed to be on the stack or what the values are supposed to be at these specific locations, you can't detect a problem. Because a problem means, oh, I'm supposed to be seeing this, but somehow the analysis tab is giving me something else. Then you know, okay, something is not right, which is going to happen soon, okay? But at this point, I'm expecting the program to do everything correctly, because otherwise, that means I just made a big poo-poo because I gave you a wrong main program to begin with, which means there's no way for you guys to test your code. All right, so let's go back and go back to the analysis tab this time and find out whether that is what we are seeing. So if I go back to the analysis tab, I will be focusing on the memory write operations, which are all going to be in column C. So we checked this one already. At location F7, we are expecting F8. That's cool. At location F6, we are expecting the content of F7. We got that. At location F5, we're supposed to see 55 in hexadecimal. I think we got that. At location F4, which is the return address, we're supposed to see 46. I think we got that too. So everything up to this point in the analysis tab is matching exactly what the map is telling me that I should be finding. Now, of course, I forgot to update. I have been forgetting to update the stack pointer for a little bit. So that means right now, this is where the stack pointer is pointing to. Well, do you think I can check that? Do you think I can check whether the stack pointer is pointing to the right location?
Yes.
Yeah, because every time we change the stack pointer, column C, actually column D changes. Okay, it tells us which register got changed and what value did it change to. So we'll go ahead and double check because it's important to double check. So we can see that register D has a value of F4 by the time we update the location F4. So we checked everything now. Okay, everything checks out. So at this point, the program is ready to do the JMPI as indicated by the analysis tab. So that means the next instruction, which is this line here, is inside traverse already. So inside traverse, the first thing we do is we want to allocate for the local variables, which means normally if you do have local variables, the stack pointer should go lower, right? But in this case, traverse has no local variables, which means it's just a stupid, cycle wasting thing to do.
Right.
But it's giving me the preparation of in the future, if I do want some local variables, it'll be easy to change the program to have local variables. So we are not expecting the stack pointer to change. You can see how the stack pointer continues to be F4, quote unquote, after the allocation. Are we still good so far? All right, so this is where the real discussion is, okay? Is what is T underscore PTR? What exactly is it and how do we use it? So, yes, go ahead.
I would expect it to, I see the LEI for the local variable size
Mm-hmm.
inputting into A, but I don't see the ones for the pointer and the array yet.
Because those are already made, it's already done. Because this is, okay, so, okay, let me show you what is happening on the stack. Give me a second.
So I know you're going to explain it, but what I'm thinking is that the call E allocates for the arguments, or is it the caller?
It's the caller.
Okay.
So the caller is the one that pushed all the arguments, and it's
Gotcha.
already here.
Right, the address.
Yeah, we got these two as arguments. This one is the return address. So the quote unquote call frame that we're referring to are these three locations.
Okay.
That's the call frame of Traverse. The call frame of main is everything else. So let me just kind of make that really clear. I can move the tree to the other side. So let me select the rectangle here because this is still important, but I don't need it right away. So I'm going to move it all the way here. And then we can go back to the pencil tool. And then I'll just go ahead and give you the range. This part here is the call frame of main. Okay. This part here is a little bit harder to describe because we end up with multiple call frames of traverse. So I'm going to say this is call frame of the first invocation of traverse. Okay? So is this working out okay so far? Having a kind of pictorial or visual representation. Okay.
The address of pointer, the address of A4, and the return address are called by
Main.
main.
They're pushed by main so that traverse can utilize
Okay.
those 3 bytes.
Okay. Thank you.
Mhm. All right. So at this point, we will also spend some time to take a look at the offsets because I think some of you may not be having a good grasp of what the offsets are about. So where this frame is, okay, these 3 bytes, where they are they here? Are they here? Are they here? Doesn't matter, okay? Because all we need to know is given where the stack point is pointing to, where do I find the first parameter? It's 1 byte away from where it points to. Okay. Where do we find the second parameter? 2 bytes away from where the stack pointer points to. So that's why it's the relative positioning of the parameters that is of importance to the callee. Because the stack pointer can be all over the place. And because this is a recursive code, recursive subroutine, so that means the next invocation, we're going to have 3 bytes down here for also for traverse. So how do we figure out, so which one is which one? Easy peasy. Because everything is relative from where the stack pointer points to. So we never confuse, and say, well, which location should we use for the first parameter? It's always going to be 1 byte away from where the stack pointer points to. Is that okay? All right. So given this particular representation, I am going to also use this graphical tool here. I know this is going to look a little bit more confusing because I have to kind of go all the way through. And I'm going to use the ruler tool. I know there's a ruler tool here somewhere. Nope, not that. Where's the ruler? I know there's a ruler. That's just an eraser. Nope, that's just color. Dang it. Well, I suppose I can draw just straight lines. I don't think it's going to draw the straight line that I want. Oh, okay, it does. Fine. Okay. So when we look at these two, okay, and then let's switch back to a regular tool, which is just a pencil. Oh, how do I cancel that? There we go. This is T underscore, what is the name of the first parameter? I think it's PTR. Is that okay? Does everybody now understand what is the label T underscore PTR trying to tell us? It's the number of bytes between where the stack pointer points to and where we can find PTR as a parameter. Is that okay?
That made it a little bit more confusing. T underscore pointer is that.
It's a label. It's really just a label. It's a symbolic name, but the
It's
meaning. Yeah, go ahead.
it's offset is 0, correct? From the
No, it's
return.
not 0. It is 1. Because at the offset of 0, it would have been the return address
Right,
itself.
right.
So it is at a 1. It is 1 byte off. Okay, this is at offset 0.
Uh-huh.
This is at offset 1.
That's where the T underscore pointer is.
That's where we expect to see pointer as the first parameter.
Oh, okay. Because that's just the address of N4. That's the first traverse. So what you're saying is after we actually get inside traverse, the first local variable is going to be 1 byte offset from the return address. Am I getting that right?
It's always going to be 1 byte away from where the stack pointer points to. So I would use where the stack pointer points to as a reference point instead of where the return address is.
Okay.
Because if I had local variables, then the the number of bytes away from where the return address is
Yeah.
versus where the stack pointer is pointing to, those two would not be the same anymore because I actually got stuff below the return address.
Okay.
So the referencing should always be based on where the stack pointer is pointing to,
Okay.
and not where the return address is located.
And are we talking about at entry point? So
This is after allocation already.
after allocation.
This is after the allocation
Okay.
of local variables if we had any.
Okay.
In this case, we don't.
Okay.
So but is the picture kind of giving you an idea of what the label T underscore PTR is trying to represent? Let me give you the other one too, because I think that might help too. So let me give you the other one, which is array. So get this. This is T underscore array. It's basically telling me if I know where the stack pointer is, I now know how to find PTR and array as parameters. Are we doing okay so far with this picture?
Are they above the stack pointer in that order, or are they
The stack pointer is still pointing to the same location.
Right. So the T underscore pointer, that's the order that they're in. The T
This is the direction where of counting.
Okay.
So that's why it's always a non-negative integer. And this is also why the stack grows downward, not upward. So the offset to access things is always going to be positive. It never goes negative. Because if the stack was to grow in the opposite direction, from low location to high location, then we'll be doing subtraction in order to get to the address of items. It's symmetric. It's not a problem. It's just that most people it's easier for most people to deal with addition to find something rather than subtraction to find something. But this is one of the reasons why the stack is growing backwards.
I'm so sorry, Professor. The green.
No need to be sorry. Yeah, please go ahead and ask.
The green is just really confusing. I don't know what I'm
Okay.
looking at.
So the green is representing, what each label is trying to define. Okay, let me try to think of an example. I know what example to use. Okay, because vacation is in our minds right now because we're getting to the end of the semester, right? So let's just say that the entire class is going on a camping trip. Okay, I know that has absolutely nothing to do with assembly language programming, which is cool. Okay, and with caravan. Okay, so each one of us is driving a vehicle. Okay, and the ordering of the vehicles remain the same. Okay, it's just protocol. You just decide. Okay, so and so is going to be the first car. So and so is going to be the second car, and so on. Okay, so that order is predetermined. Are we good so far? And wherever we go, okay, there's a we can order stuff from Amazon. You go like, how can Amazon find any one of us when we're going camping? So as it turns out, the first car, let's just say I'm the first car, okay, of the entire caravan. And when we park at the campsite, we follow exactly the same order. Okay, Tack is the first car, Rayshon is the second car, and Manpreet is the third one, and then Marcus is the fourth one, and so on. Okay, so we follow the same order everywhere we go. So I'm the only one with a GPS. Okay, in other words, they can find me. Amazon says, yeah, we know what Tack is. So let's say Rayshon is trying to order something from Amazon, and your car doesn't have a GPS, so you can't really say, okay, my absolute location is here. You don't have a GPS. You cannot say that. But you can say, I know you guys can find TAC because TAC's car has a GPS attached to it, so we can always locate where TAC is. I'm the third car down from this caravan.
Okay,
Does that make sense?
that makes sense. So
So
the
okay, wait.
go.
But the analogy is not done yet. Okay, so we're done with one particular campsite. We go like, oh yeah, we're getting bored with this campsite, so we packed up and we go to the next campsite, right? When we get to the next campsite, you decided, darn it, I left behind my favorite blah 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 in the previous campsite. I need to order that again from Amazon, right? So how do you specify where Amazon can deliver your stuff? The same idea. I'm the third car behind where TAC is. Because TAC's car has a GPS, which is equivalent to where the stack pointer is pointing to.
Right.
So they can always find me.
Right.
But because your car is always the third car from my car,
Right.
so if you just say, I'm the third car from TAC's car, and you know how to find TAC, right? Amazon says, yeah, we know how to find TAC. So now they can find you too. Okay, I'm not sure whether that is improving or making it even worse. Yep.
What labels do we increment the stack pointer by to get to PTR?
To get the PTR?
Yes.
Well, PTR is just a label. TPR is basically defined to be one. It's literally really just the symbolic name of one. T underscore array is the symbolic name of two. So this way, the idea of using label names instead of one and two is I don't have to remember who's one and who's two. Once I set up the label definitions, where is the? Yep. So once I figure out the label definitions, okay, not right here, but going back here. Once I figure out the label definitions, I don't have to remember which one is the first parameter, which one is the second parameter, which one is a local variable. It doesn't matter anymore. It's just like instead of remembering the third car, from where TAC is, it's Rayshon's car. So instead of having a number on my list of who is at which location, I just have to remember Rayshon, Manpreet, Marcus, and so on, Anthony, and so on. I don't need to like where is that car? Is that 5 or 6 away from me? Nope. I just have a symbolic name. Is that okay? That's what the label is for. It makes it easier for me as a person, as a human, to find the right offset to get to that thing. Because otherwise, if I don't have the labels, then I have to keep track of all those relative positions, which is not going to be easy. Yep.
So if the return address is where the stack pointer is pointing to.
In this case, yes, because we don't have any local variables. If we had local variables, then the return address would not be exactly where the stack pointer points to, because the stack pointer points to the last local variable that I allocate. And the return address would now be at some positive offset from where the stack pointer is pointing to.
What's the offset for TLVS then?
LVS is representing the number of bytes for the local variables. In this case, it's 0.
Okay, thank you.
So we do okay so far?
Yes.
All right. And of course, after this entire lecture is done, all people can remember is camping trip, TAC has a GPS, and that's about it. Yes.
Just kind of segue, but I was looking at the swap one that we did, where that had one local variable T.
Yep.
So that one was allocated because it's the last thing. It's the local variable. It's at the bottom. So
Right.
that one is initiated. That label is set to 0.
Yes.
And then, the next thing, which would have been the local variable size, is that one offset from that local variable.
Right.
And then, okay.
Yep. So it's a good idea to revisit that one. So I'm going to hide this one for now. So if we go back to the swap example, what we have here is we have local variable t, then we have the return address, and then we have the first parameter. Is it called PTR1 or just P1?
PTR1. Yeah.
PTR1, and then we have PTR2. So in this case, this would be at an offset of 0 because after we do the allocation for local variable, the stack pointer is pointing right at the only local variable that we have.
Right.
This is 1 byte away, this is 2 bytes away, and this would be 3 bytes away.
And that would be the only place it would make sense to point to, because if it was any higher up, then we would just essentially lose.
Well, if it's okay, if I understand your question correctly,
Mm-hmm.
anything higher up belongs to somebody else.
Well, I'm saying it would make sense for D to point to the last.
The last. Yep.
Because if it pointed to the return address and we have a local variable in this sense, then it just gone to the gremlins.
Right.
Okay.
Because so basically we want the stack pointer to always point to the leader of the entire caravan.
Okay.
Because we only want to say how many cars down from the first car to find whoever is in this particular caravan.
Okay.
Yep. Are we good so far? All right. So let me erase just that part. Okay, the part that we that I just added here. Okay.
I guess what makes it confusing is like we talk about from part first to last, but like from the bottom up. So it's kind of hard to like, not hard, but it's tricky.
Yeah, so we need to. So if I am confusing, you have to ask me: are we talking about a low memory address or high memory address? Yep.
Low as in
There's no lab today, right?
There's no structure lab today. Yep, we are. This is our last instruction day for this class. So I don't have any lab prepared, but I think this material is really important. So I would much rather use the lab time to kind of extend the lecture. All right, so we can take a break because I know this is taking up a lot of brain juice. So I want you guys to have some time to replenish your brain juice before we continue. Yep.
I have a question. So in the buffer area, there's nothing there. There's no
Not yet.
information there. It's just,
Not
it's
yet.
just safe space.
Yeah, exactly. We're just reserving that space. So okay. So just to get to that question, and then we'll take a short break. So in the C code, where's my mouse pointer? There we go. So in the C code, this line is what is going to put stuff over there. So that line is going to be an interesting one to explain, and it's going to take a little bit of time because we still have one bug that we have to kind of figure out. Because I claim that when we try to push the L member of the structure that PTR is pointing to, we got the wrong place, right? So we'll have to fix that one first, and then we move on to line 14. So let's go ahead and take a short break. How does 10-minute look? Is that okay? Yeah, 10 minutes? Okay. So we'll go ahead and take a 10-minute break. And I cannot pause the recording. I can stop the recording, but I can't pause it. I don't know why. I vaguely remember OBS can pause a recording, but I can't find the interface to do that.
OBS is too powerful tool.
For mortals. Yeah, it's not for mortals, man.
So, Professor, while we're off the record, do you mind if
It's not exactly off the record. Give me a second here. Remember to unmute the mic. All right. So, where are we in the coding? Okay. So now we have worked all the way up to um, how we computed, what is t underscore ptr, and how we get to each one of these lines here. So we have to observe line 21, 22, and 23 in the trace. So let's switch back to the trace right there. Okay, so this is why I added that feature. Just this semester, column F reports back the line number. Column G gives you the entire original line because this way I don't have to go back and forth all the time. So line 21. Okay, so let's focus on line 21, which is at location 08. It is loading the value of the label T underscore PTR into register A. That is representing the number of bytes from where the stack pointer points to where I can find PTR as a parameter. Is that okay? So the way we know this is because we drew a map for this entire thing already. So this is the map that we drew, and the stack pointer is still pointing to location F4, and what we need, which is PTR, is at location F5. So obviously, to get to location F5, we just have to add 1 to F4, which is where the stack pointer is pointing to. Is that okay? So when register A is a 1, it's just an offset, okay? It is not an address. It is simply saying, Rayshawn's car is 3 behind tax car. It's that 3, okay? Is that okay?
Yes.
All right, so next, what we do is in the C code, we have the add AD. So if we go to the actual trace, the add AD instruction is adding register D, which is F4, to register A, which is 1, and we end up with F5. So that is equivalent of saying, where's Rayshawn's car? Rayshawn's car is 3 cars behind tax car. Tax car is right here with a GPS location, and then Rayshawn's car is just 3 behind that. Obviously, that's a vector thing. We have to know which way to count the 3 car lengths, but we'll just assume that we know which way to count. Is that okay? So by adding a register D to register A, we end up with the actual address of parameter PTR in register A. In other words, we know where to find Rayshawn's car. Is that okay? All right. But the C code is not really just interested in the location, because if you look at the C code right here, so if you look at the C code, it is not asking where do we find PTR, it's asking what is PTR? What is the value of PTR? So that's why we need to dereference, because we have the address after the add AD instruction, but that will only give us where in RAM do we find PTR, but I need to know what is in PTR. And that's why in the trace here, we have this LDAA instruction, and after the LDAA instruction, we end up with 55 in register A, which is the value of PTR, which by itself is a pointer to a struct node. Go ahead.
Quick question: are you recording?
Yes, I have been recording all along because I didn't find the pause button.
Okay.
So I just muted, the mic, when we were talking.
Okay. Just to make sure.
But thanks for checking. So are we good so far? I mean, is this explaining, what we have been doing for those 3 specific lines?
We want the value of the pointer, which is itself pointing to an address, correct?
Yes, but we don't care at that point. We just want to know whether PTR is 0 or not.
Okay.
Now, whether it is a pointer or whether it is representing a counter or something, I don't care. I just want to know, is PTR as a parameter, is it 0?
Okay.
So by the time we know PTR is 55, then we use the AND AA instruction. So the effect of using the AND AA instruction is also represented in the trace, because this is what happens when we push the value 55 through the ALU. The C flag doesn't make sense, or the Z flag makes sense, and we know the Z flag is a 0 in this case because 5 is not 0. The Z flag becomes a 1 if and only if the result of the ALU is 0. And because it is not, the Z flag is 0. I know it sounds awfully confusing when I say the Z flag, which is representing whether something is 0 or not, is itself 0.
So
But
0 does not mean 0.
so if Z equals to 0, that means the value of the last operation through the ALU is not a 0. It is a non-zero. So are we good so far with the AND AA instruction? Okay. And then after that, we decide, okay, if it is 0, if the Z flag is a 1, let's go to AND if 1. Well, but the Z flag is not a 1, so we do not. So instead, we continue on the next instruction and say, well, I guess we have to do the recursive call, blah, blah, blah. And now we put the offset to find parameter array into register A, which is 2. And once again, we are looking at an offset. This is basically saying, oh, manprint is two cars behind tag. That's the 2, okay? And then in order to find out exactly where manprint's car is, we have to say, oh, let's find out where tag is. And then we can say, oh, now we can find manprint's car. So we are adding the 2 to register D, which is still at F4. So we end up with F6, in register A. Now, you can also go back to the map that we saw earlier and say, what is that F6? Aha. So that is indeed the second parameter, which is called array from the perspective of the subroutine. Okay? And then we say, but we are not interested in the address of parameter array. We're interested in the value of parameter array. So we need one more LDAA to do a dereference, and that turns out to be F7, and then we push it on the stack. So now we push it on the stack, and how do we know? Because we have this thing here. Okay, this is representing that we push array on the stack. So back to the picture, I can now adjust the picture to represent this too. So now I say, we have one more byte on the stack now. We're pushing array again. So this is actually array, which is also just the address of PTR. Wrong color. And that is F7. This is location F3. So it is location F2 that is problematic. So for that, we have to go back to the source code first to find out what we are supposed to push on line 13 in the C code. Okay, let me go back to the C code. So we are supposed to push the member L of the structure that PTR, which is our first parameter, is pointing to. Not the address of, but the value of. Is that okay? So the first thing we need to do is to access PTR, right? So if you go to the assembly code, this is where we have a little bit of a problem, okay? So I put T underscore PTR into register A on line 34, and that one we can track it in the trace too. So we basically say, this is what it is, okay? You can see the big to-do, the all, cap, to-do. This is where the problem is. So I am putting a 1 into register A, and that 1 is supposed to be the number of bytes between where the stack pointer points to and where I can find the first parameter. But let's take a look at what is happening on the stack right now, because that should explain why it is a problem. Because the stack pointer is not here anymore. The stack pointer, after we push the second argument, the stack pointer is actually here now. All right? So you can see that, so that means everything, all the labels are now wrong because all the labels were created when the stack pointer was pointing here. The stack pointer is now pointing here because I just pushed something on the stack. Is that okay? So what am I supposed to do? Well, all you have to do is to track. That's okay. No need to panic. All we need to do is to figure out how many additional things did we push on the stack compared to right after we finish allocating for all the local variables. So you go like, okay, this is where it's supposed to be. This is where we are. It's off by 1 byte. Is that okay? So now, when the program does not fix for that, doesn't account for that 1 extra byte, oops, what happens is it's now thinking, this is my first parameter. So it's going to use the return address as if it is the first parameter, which obviously is going to create all kinds of problems. Okay? But we want to double check that the code is actually doing this. So what it will end up doing is to think this is the first parameter, which is supposed to be the address of a struct node, and we want to access the L member of the struct node. Okay, so the return address is at location 46, right? I mean, this is at 46. So it's going to look at 46 as the address of a struct node, and then they go like, let's check out where the member L is supposed to be at. And that is defined by a label. So let me mark this first. So the label L is supposed to be the second item, so 1 byte away. So it's going to think that location, okay, let me get back to the picture. So it's going to think that location 47 is where we find the L member of the structure pointed to by PTR. Is that okay so far? Now, how do I know whether the program is incorrect the way I describe it? I follow the trace. Okay, so we'll keep going in the trace itself. So the way we do this is we go to the assemble tab because we want to find out what is at location 47. So location 47 is DF. This is the value at location 47. Obviously, it is not a part of a struct node, but the way the code is working right now is to think that 46 is the first byte of a struct node, and then 47 is where we find member L of that struct node. And it's going to push DF on the stack. All right? So this is the expected wrong behavior. I know it is wrong already, but I want to know exactly what it is going to do. So now we go back to the trace again using the analysis tab and see if that is what we're pushing. There we go. So it's erroneously pushing DF on the stack instead of, I think it's supposed to be a 0 in this case. So is that okay so far? Okay. So this is before we fix the problem. And I can go ahead and fix the problem, rerun this entire thing, and it will change a few things still, but it will change this to become 0, 0. Because that is supposed to be the L member of the structure that PTR is pointing to. Are we doing okay with this? Okay. So let me go ahead and fix the code. There we go. And we have to go.
Professor, sorry.
Yeah, go ahead.
After you fix it, could you show us where in the C code we are? Because I'm a little lost.
Sure. So we are basically trying to. Yeah, this is where we are in the C code.
Okay.
And it's erroneously. It doesn't. It's trying to figure out where PTR. What is the value of PTR?
Mm-hmm.
And that's where the problem is. Okay. It's using the return address as if it is parameter PTR
Instead of the value.
instead of no. It's using. So the location of the return address is being used as the location of PTR erroneously.
Okay.
Because the stack pointer is 1 byte pointing to 1 byte below where it's quote unquote supposed to.
Okay.
So the fix to this problem is simply to do the 1+, because we have one extra byte on the stack. In other words, we have one extra byte between where the stack pointer points to and where the first parameter is. So having this one extra plus one is going to fix the problem because now we know the correct offset or number of bytes between where the stack pointer is pointing to and where we are supposed to find parameter PTR.
Okay. And it moved because we pushed something.
Correct.
What did we push?
We pushed the second argument. This is the push
Okay.
that we did that ended up with this one, at the wrong place.
Right. Gotcha. Okay.
All right.
I have a question.
Yep.
Could we not just put T array?
Hmm?
Could we not just put T array?
You could, but that would be conceptually incorrect because we really are trying to push PTR, and I would rather my code to reflect what the intent was.
Okay.
So that's why it is important to keep using PTR and not array. I mean, just the fact that we are tracking array is one more than PTR kind of defeats the whole purpose of using labels too, because the whole idea of using labels is so that I don't have to keep track of those numbers in my head. Like, which one is the first parameter, which one is the second one, which one is a local variable. Once I use labels, I don't care because it's the same way to access all of those items. All right, so let's give it a try. And the interesting thing is because this is just a change of an expression, so it doesn't really change anything else with the code except it would just do the right thing and push a 0. Are we doing okay so far with this? It might take some time, to rewatch this, and then try to kind of grasp the idea. If you want to, you can also kind of take a snapshot of the assembler at this point if you want to, or when we are done with this. So this way you can kind of, without having to run River Spider, you got all of this already. Then you can just go ahead and print it out, put it on a piece, print it on pieces of paper, and then you can comment on the piece of paper. So some of you may find it more easier to do rather than just looking at the screen. All right, so where are we now in terms of the coding? We are now done with line 13, so we can move on to line 14. So line 14 is kind of the difficult one in a way, but it's also, the one that is, it doesn't have a recursive call. This is just, doing an assignment operation. All right, so the way we do this is, it would seem to me that the left-hand side is a little bit trickier than the right-hand side. So we're going to do the left-hand side first. Okay, we'll find out where we are supposed to store the right-hand side before we go ahead and process the right-hand side. Is that okay? So this is the opposite of what I usually do because I usually would compute the right-hand side first. But this time, let's deal with the left-hand side first. So one thing you need to know is, I just did something I'm not intending to do. So one thing you want to know is this thing here is really the same thing as not having this increment, and then later on on the next line, do the increment here. It's the same thing. So if you are wondering, when am I supposed to add that one to what array is pointing to? This is the same thing. Okay, this is equivalent to the original code. It just looks a little bit differently. And that's because it was a post increment, which means the increment is not supposed to happen until the expression is fully evaluated. Okay, as opposed to a pre-increment, which is supposed to happen before the expression is evaluated. So this helps, right? Because this does make it a little bit easier to understand. It's like, oh, okay. So we can worry about the increment later on. We'll just kind of focus on all that crazy dereferencing, okay? All right, so we'll deal with the crazy dereferencing. So after the post increment is gone, you can see this is a dereference. So is this one. So basically, we just have double dereferencing. I think that's not too hard to deal with, because if we know how to do one dereference, we can dereference again. So in the assembly code, we'll deal with the left-hand side. So I'll make it a point of this is the left-hand side of line 14. So that would be, okay, we need to get to array. So LDI a with T underscore array, add AD, okay, because the first line LDI is only giving us the offset. Now we have the address, and now we have the array, okay, we have the value of array, which means at this point, we got this in register A. Okay, looks like we need to dereference one time, okay, to take care of this particular dereference, right? Come on, highlight. There we go. So this line is corresponding to this particular asterisk here, and then we need to do it one more time. But wait, I don't want to do it one more time yet, because the next time we dereference, we are trying to dereference it like this. We need to know what we are supposed to store before we do that one last dereference. Because every time you see register A or whatever register in parentheses, that counts as one dereference. The only question is, are we reading from where we're dereferencing to, or are we storing to where we're dereferencing to? If you're reading, you're using LD. If you're storing, you're using ST. Is that okay? So I can't do the last dereference unless I know what I'm supposed to store yet. So let's go ahead and figure out what we're supposed to store. So the right-hand side is just the member value of the structure that PTR is pointing to. So we need to get to PTR first. So LDRB, I cannot use A anymore because register A contains the address where I'm supposed to store something. So I have to use register B or C in this case. So it's going to be T underscore PTR, add BD, LDBB. So that would get me to just PTR. But what PTR really is the address of a struct node, and I want to access the value member of the struct node that is pointed to by register A at this point. So I need another register, so I barely have enough registers to get this done. So I use register C to store the offset from the beginning of a struct node to the member that is called value. And then we add that to register B. So register B now becomes the address of member value of the structure that PTR is pointing to. Great. Just one little step to go, right? Because the code here is not saying, let's get to the address of that member. We want to get to the value of the member. So we have one additional LDBB to do before we get to that. So when we have this, then we have register B storing the right-hand side. Register A, as we talked about a little bit earlier, is the address of the left-hand side. One store will finish the actual assignment operation. So that is corresponding to line 14 after we break up the post increment. Okay, I'm just going to pause here because this is quite a bit of stuff already. So I want to make sure that we are feeling okay with this, comfortable with this. And I'm going to ask you guys, can we test this? Can we make sure this is working before we go any further? We can indeed, because we know the value of N4, right? So that means we are supposed to know exactly what happens when this code executes, which location is going to be changed to the value member of N4. We go so far. All right. So which location are we supposed to change? Array is the address of PTR of main. So this is PTR of main. It is a pointer pointing originally to the beginning of buffer. And then array inside the first invocation of traverse is the address of PTR. So that's why we need a double dereference to get to a location in buffer, because the first dereference will get us to PTR. The second dereference will have PTR pointed to somewhere within buffer, which is starting at the first location, the first byte. So, so that means if I run this code as it is right now, okay, let's go back to the map again because that memory map is really kind of handy. Okay, so what we are supposed to do now, okay, N4 is actually also on the projector right now. So N4 has a value of 4, okay? That 4 is supposed to store to wherever double dereferencing the second parameter of this call. Okay, so at this point, we are done with the recursive call already. So let me just refresh you what is supposed to be on the stack at this point so that we have a correct discussion. So all this stuff is done. This is all done. We are now back to the first invocation of traverse because the second invocation is already done. So with this one, we now try to figure out what are we supposed to be overwriting and what we're supposed to be overwriting it with. We know the right-hand side of the assignment. Let me go back to the assignment operation. So we know the right-hand side of the assignment on line 14 is going to give us 4 because that is the value member of N4, and the address of N4 is PTR in this case. Okay, so that's supposed to be 4. Where are we supposed to store that? So let's check out. Okay, we'll use the map to help us figure that out. Okay, so we are double dereferencing the second parameter. This is our second parameter, right? This is the return address. This is our first parameter. This is our second parameter. First, the reference is go to location F7, find out what it is. This is location F7. It has a value of F8. Second, the reference. We go to location F8 and store 4 over here. That is supposed to be, that's what it's supposed to do. Is that okay? Let's draw some lines, okay? Let's draw some arrows. And we'll go ahead and pick a different color this time. Okay. So we are looking at, I'm just double checking, make sure that I'm using the right tool. Yes, I am. So we are basically looking at this thing, using this thing as a pointer. First, the reference goes here. Second, the reference, it goes here. So it is at this location that we should store a value of 4. Are we doing okay so far with understanding why I think location F8 should become 04 with this addition of this source code? Okay, so once I know what it's supposed to do, I can check whether it's doing it or not. So let's go ahead and do that. So we go back to this code, make sure it is saved. Okay.
Can you, so the 4, is that what, in what we see here represents the 4? Is that the node in the assembly code?
In the assembly code?
Yeah, where's that 4 value?
That refers to, so that 4 is referring to PTR points to value. Because PTR has the address of N4, and the value member of N4 is 4.
Then on the assembly side though.
I think it's node value.
No
right?
value, is that what's 4?
I believe it's node value.
No. Okay, so going back to, let's say what each line is doing, starting with this one. B has the offset of PTR. B has the address of PTR. B has PTR. So right now, okay, on line 57, B has the address of a struct node. So which means B is a pointer pointing to the beginning of a struct node. In this case, it will be N4 as a struct node. Line 58 is adding the offset from the beginning of a struct node to the member value of the same struct node. So by adding register C to register B, I now end up with the the address of member value of the struct node that is pointed to by PTR. So in essence, by the time we get to line 59,
Mhm.
register B should contain the address of the value member of N4 as a global variable.
Mhm.
So one dereference means I'm actually getting the value of the member value of the structure N4, struct node N4. That's why B is 4
Okay.
by the time we get to the store instruction.
Where is that 4 stored? Is that in the
It's the value member. It's the value member of N4. So in the code, okay, I have to remember where I'm here. So
in memory though? Where is that 4 sitting?
this is where the 4 is.
Okay.
Because it is the first member of a struct node. A value is the first member of a struct node.
Mhm.
So N4 is initialized with 4 as its value,
Okay.
and then null pointers for L and R. That is corresponding to this here in C code.
Because the byte thing is a little confusing for me because I don't see it on the opcode table or whatever, and this byte just means that value.
Byte means you'll allocate 1 byte, and this is the value of that byte.
Okay. All right.
That's all it means.
Okay.
Yep. And you can also check out what byte does using the assembler. So if you switch to the assembler and you switch to the assemble view, that would actually give you a pretty clear picture of what it does. So if you keep going down, down, and this is N4, location 55 is 04, location 56 is 00. In other words, all this does is to say allocate 1 byte, and 4 is the value of that byte. Allocate another byte, 00 is the value of that byte, and so on.
And location is 55, right? So that's way
Correct.
down. That's
This is
way
location.
Down, way down in the memory, right? We're at F
Yes,
something,
it
so
is
that's
way down.
there.
Yep,
Okay.
it is way down. So looking at this picture, that means we are expecting register B eventually to be 55, and then that's how we got, and then it became 04 because we dereferenced register B once. Is that okay?
And how does it know to go to 55?
It knows how to get to 55 because PTR has a value of 55.
Okay.
So let's go back to the picture because that is actually in the picture itself. See this 55 here?
Okay.
That's the first parameter.
Gotcha.
So the first parameter has 55 already because it is the address of N4. So using that, we now get to the actual location 55 to retrieve the 04, and then we copy that to the first byte of buffer, which is at location F8. So we are expecting location F8 to update to 04 when I run this code. All right, so let's switch back to the command line and just test run it and see if that is what it is, how it's behaving. All right, and then switch back to the analysis tab. All right, so this is the recursive call. Okay, the recursive call is not going to do anything because we are passing a null pointer, so it should return relatively quickly. And here it returns. Oh, this is the actual recursive call, and it skips over the conditional statement. This is where it returns. So we are back to, okay, so let me be more clear. This portion here is representing the second invocation of traverse. Now, the second invocation of traverse has PTR being 0. So it's skipping over the whole thing and get to the end really kind of quickly. And then as a result, we return back to the first invocation of traverse. And this is where we return to in the first invocation of traverse. Is that part okay?
Because the and AA makes the Z flag 1, so then it jumps to end at 1.
Actually, I take it back. Sorry, I take it back. So we are not quite back yet. Okay, this is how it skipped over the entire then portion of the conditional statement. This is after the conditional statement, and this is how it returned back to the first invocation. We doing okay so far? Because you can also look at the line number and figure that out. Because everything is sequential, right? Over here, you can see how all of these line numbers are sequential. So that means we're keeping going forward, and you can see also a big jump of the line numbers from here to here. That's because we're skipping the then portion of the conditional statement. And then by the time we get to line 71, that's the end of the subroutine. So this portion here really marks the execution of the second invocation of traverse. So we have the first invocation of traverse using up some stack space. Then we have the second invocation of traverse using up some additional space on the stack. But by the time we are done with this, we're back to the first invocation. So this is back to the first invocation, and it's cleaning up the two arguments. And we verified that it's working up to this point already. So what we are trying to verify now is from here all the way to the actual update of that location up to here. That is the line that we are implementing right now. So this portion here is corresponding to line 14 in the C code. The highlighted portion, all this stuff here, starting with row 113 all the way ending up with row 134, that is corresponding to the new code, which is implementing line 14 of the C code. Are we good so far? Okay. So we verified that we put a 404 at location F8 as expected. So that's good, okay? Because that means we got one more instruction done. One more line of code done. So what is left to do? Because this line here, line 16, is no biggie, right? We just kind of copy and paste the one for line 13, change that L to R, we're all good. So we now have to do line 15. So let's go ahead and finish line 15, and then I'll just kind of copy and paste a good portion of the other part, and then we are done. All right, so we are now trying to implement incrementing what array is pointing to. Is that okay? So that means we have to figure out where it is first. So LDIA with T underscore array. Oops. There we go. Add AD. We got to the address of array. Now we have array. But this time I have to be careful because I want to get to what array is pointing to first, but I don't want to destroy A. A is going to be useful. So register B is the value that array is pointing to. I load it into register B. I increment that particular value, and then I store it back to whatever array is pointing to. So once again, it is super important to keep track of which register has what in each one of these instructions. It might take you some time, after class to kind of go back and review this, but the trace helps, okay? Because with a trace, you can actually see, oh, okay, register A has this right now, then it has that, then it has that, and so on. So I'm just going to verbally go over this: offset, address, actual value of the parameter, what it points to, increment what it points to, store it back to where array is pointing to. So as a result, we actually end up incrementing what array is pointing to. Now, I can say that all day long, but we want to know whether this is actually what's going to happen or not. Okay, so that means we have to go back to the map and find out. So what is supposed to be incremented by 1? So we want to go back to the map first and figure out, what is supposed to be incremented by 1. So when we get back to this map, we are looking at the second argument, which is also just this one. Okay, where? Oh, there we go. So we are looking at the second argument and say what it points to is supposed to increment. So this thing points to this location at F7. So we are expecting F8 to become F9. So we are expecting this value here to go from F8 to F9. That's what we're expecting to happen. So we'll run the code and find out whether the new code that we just added is going to accomplish this or not. Is that okay? Are there any questions about what I'm expecting the program to do? No questions? Okay. No further questions.
That was that far.
Hmm?
Don't go that far. There'll be some further questions.
There'll be.
It's not right. Prosecutor.
All right, so we go back to the trays and we just kind of keep going down a little bit. And at some point, we should see F7 is getting updated to the value of F9 right there. All right, so we are almost done, right? Because all that is left to do is to copy a section of code from the beginning to after this chunk of code, change the reference to L to R, because we are updating, we're passing the R member of the structure pointed to PTR instead of the L member in this case. All right, so we're getting pretty close. Okay, so just stay with me for a little bit longer. So I put a marker here so I can remember where that is. And then we just locate the chunk of code that we are supposed to copy and paste. That would start with line 28, ending with line 49, 28 to 49. And Y means yank. So now we can paste the yanked code and have to remember to change the reference of member L or the offset to member L to the offset of member R. And that's it. I mean, that's pretty much it. I mean, the rest can stay exactly the same. All right. So are we ready to test run this code?
Yes.
Okay. It would not make much difference, okay, because both the left and the right are null in the case of F4. So we are not going to expect the program to do something that's dramatically different. It would take a little bit longer. There will be more items, but we ended up with exactly the same locations changed exactly the same way. Okay, so if it doesn't do that, something else is wrong. So we go run it again. And then we get back to the trays, and we just have to verify that nothing bad happens after this point. This is fine. This is the recursive call. We still have to push the second argument, the first argument, the return address, and then there should be no further update on the stack whatsoever. So we just double check, nothing happens. The stack pointer returns back to 0, 0, everything is balanced, and we do end up with a halt instruction as intended. So we're good. I think the algorithm is all done. So now the only thing we need to change is to change N4 back to N1, okay? Because that's the most complex case. So before we do that, I do want to explain what it is supposed to do once we make that change. So the way it, okay, so the term traverse is basically a term to describe how you visit from one node to another node when you have a tree structure like what we have here. So this is called a tree structure because there are no loops and there's only one way to get to one vertex, each vertex. Okay, so that makes it a tree. So the way it works is it will start with N1, then it will go to the left-hand side of N1, which is N2. It will attempt to go to the left-hand side of N2, but there's nothing there. And then at that point, it will store the 3 into the buffer, and then it will traverse the right-hand side of N2. So it will end up at N4. It will try to traverse the left-hand side of N4, nothing. store the value of 4, which is the second item in buffer. Then we try to traverse the right hand side of N4, which is also nothing. Then it goes all the way back here. There's nothing else to do. Go all the way back here. Then we try to traverse the right hand side to N3. Then it would try to, it always prefer to traverse the left hand side first, if, and then the right hand side. So when you get to N3, it goes to the left hand side, which is N5. Then it will try to traverse the left hand side of N5. There's nothing there. Go back to N5, store the value of 9, and then it will try to traverse the right hand side, which is also nothing. Then it goes back, go back, and it will try to traverse the right hand side of N3, which is also nothing. Oh, excuse me, I take it back. It will store 10 first before trying to traverse the right hand side. So in the end, it's going to store these numbers in a sorted way. So it's going to store 3, 4, 5, 9, and 10 in that specific order to the buffer. Is that okay? This is a binary search tree, and we are just traversing it so that we retrieve what each node has as a value, and then store those values into an array in that specific order. Okay, so we go back to the code here, and then we just change the reference of N4 to N1, and then we'll see if that does what it is supposed to do. So N4 changes back to N1, save the file, run the whole thing again. So this time, the way I'm going to track down, whether it gets the right thing done or not, is to look into all the right operations to the buffer. So we'll go ahead and go back to, I just bypassed that. There we go. So we get all the way back to the trace, and then we'll start from the beginning. We are looking at column C, and this time I have to specify what I'm looking for. This is a little bit advanced, but you can also do it manually. So I'm going to use regular expression to say, whenever we update anything from 8, 9, A, B, C, D, E, F, let me know. Because all of these locations correspond to a location in buffer. Is that okay? Everything else, I don't care. Okay, I really don't care if it updates other things on the stack because it's pushing the return address or it's pushing all the arguments and whatnot. I'm just focusing on what it is putting into buffer. So now we have to specify we are searching using regular expression, and then click find. So we store 3 to the first location in buffer, 4 to the second location, 5 to the third location, 9 to the fourth location, and then 0, 8 is basically 10 to the last location. So the program is now doing exactly what it is intended to do. And that's it. All right, so what is the takeaway? I mean, this is a pretty long lecture, I understand that. But what is the takeaway? I mean, how is this going to help you prepare for the final exam?
It does a lot. Well, first of all, the traverse function, it was a little bit complicated because it uses the comparison, or it uses branching. So that was helpful right off the top. Um, it also shows because all of those N1, N2, N3, their labels are defined with bytes, so it helps you visualize what bytes are, and then help the pictures definitely tremendously help with showing where pointers are pointing to, what addresses are what, and what it's doing. So it all comes down to the visualization of the buffer. And that's the thing that,
well, that's part of it, yeah.
Well, I mean, it's at least for me.
Yep.
That's one thing that I'm missing when I study is drawing the buffer. I'll draw it, but then I don't know what is where, what goes where, and what's going on. So then it's once you know what's supposed to happen with the buffer, then the assembly language almost kind of falls out, naturally, because you can kind of know how to you know how to load a value
Mhm.
into a register, you know how to push things onto the stack and all that
Mhm.
stuff, but it's like what order is all dependent on your visualization of the stack, and that's what helps the most. I think
Okay.
the picture.
Yeah, there are a few key concepts. Okay, remember, we talked about abstraction and generalization. So the few key concepts. One is what is a stack? Okay,
Mhm.
well, the stack has a stack pointer. The stack pointer is basically defining a border
Mhm.
of which part is in use and which part is not in use. So what can we do with the stack? Well, you can push, putting more stuff on the stack. You can also pop or deallocate, getting rid of stuff on the stack. Okay, to push is to decrement the stack pointer. To pop or to deallocate is to add to the stack pointer. Okay, so those are stack related concepts. Then we have function calls, right?
Right.
So when you call a function, the reason why a subroutine knows where to go back to is because the caller is pushing the return address.
Mhm.
And then the agreement between the caller and the callee is the last thing that I push is the return address.
Mhm.
I might have pushed some other additional items called parameters, but the last thing that I push is definitely the return address.
As a caller.
Hmm?
As the caller.
Yes.
Yeah.
And then the callee can count on that and
Mhm.
say, well, when I'm all done, and
Mhm.
I need to continue execution where you left off,
Mhm.
I know where to find the address that I need to continue on in order to get back to the caller.
Right.
So that's the callee, the call return kind of relationship. Third concept, arguments versus parameters. So arguments is what we see from the perspective of the caller before we continue execution of the callee. Those are called arguments.
Mhm.
So the caller has to set up all the arguments. But by the time we get to the callee says, well, in order to do what I'm supposed to do, I need to know blah, blah, blah. Okay? So now, from the perspective of the callee, it's trying to access the parameters. So once again, we have this agreement of the last argument is pushed first, which means the last argument really sits up at the highest portion of the memory,
Mhm.
and then the first argument is right next to the return address.
Okay.
So based on that agreement, the caller and the callee can now communicate using the stack.
And if there are any local variables that's under the return address, or
Yes.
one offset lower than the return address.
One or more, depending on how many
Mhm.
local variables you have,
Right.
those would go below where the return address is,
Okay.
because only the callee knows, how many bytes are needed.
Right.
The caller doesn't care. So that's that part. And then when we need to access either local variables or parameters from the perspective of the callee, we utilize the labels because it is nice to keep track of how far away each item is from where the stack point is pointing to. So we're using the stack where the stack point is pointing to as an anchor.
Mhm.
So we are basically going like, yep, this thing is 5 bytes away from the anchor. This thing over here is 3 bytes away from the anchor. So this way, the entire frame, the actual absolute location of the frame, doesn't matter.
Right.
It doesn't matter where the caravan is. Okay, we can be visiting the Yellowstone National Park. We can be over at Yosemite and whatnot. It doesn't matter
As long as
because
you find tax card.
as long as you can find tax car and then the ordering of the rest of the caravan is maintained. That is the caller callee agreement. Okay. So once we understand all of those concepts, then we have to figure out how to use the instructions of tax-toy processor to do each thing. LDI is great to put an offset into a register. Add AD is great for adding the stack pointer to an offset. LD is great for dereferencing. Hey, you got an address there, but I really want to know what is at the address. That's LD. ST is exactly the opposite. We need to update that location, and I know exactly what value to use to update that location. That's ST. So those form the core.
Could you repeat that? I'm sorry. Could you repeat that about ST?
ST is storing to a location that the register is pointing to.
Right. So that's the value. No. That's the address.
You always have the address with the register in parentheses.
Right.
and then the other one just contains whatever value you want to store to that
Into
location.
address, okay.
So going over the opcode table can be useful because the opcode table column C is using a C notation to indicate what the instruction is supposed to do.
So I have a question. So looking at that, the R local variables, are you decrementing the stack pointer to put those on?
Yes, you have to decrement or decrease the stack pointer to account for the number of bytes that you need for your local variables.
And then when you're done, you pop.
When you're done, you deallocate. You don't quote unquote pop because the word pop implies that you are utilizing the value of those portions of the stack. But by the time you're done with the subroutine, what the values are with your local variables doesn't matter anymore. I mean, all you're trying to do is to say, I don't need this anymore. I'm just bumping the stack pointer back up to where it points to the return address. So a good thing to do with this class is to go over the swap subroutine, but using the same way that I did with this particular program. So go through the trace, reconstruct the stack, reconstruct the content on the stack as you execute the code, as you follow the execution of the code, reconstruct what is on the stack and figure out what is this over here. I know it is just FE, but what is FE representing? Oh, so that's the address of local variable y of main. But why is it over here? Oh, because it is an argument. We just pushed it on the stack. How do we access this from the subroutine swap? Well, we know where the stack pointer is, and then we define all of these offsets to the different items. That's how we get it back. So you can repeat what I did with this program with swap, and this time it does have a local variable, but all it does is to change the offset of where the stack pointer points to the various items in the same call frame.
Right.
Yep.
Okay, so I have two questions.
Yep.
So, okay, I guess I'll start off with, so if we ran traverse with the address of N3, would buffer then just be 9 and then 10?
Let me take a look. So you want to change the call from main to use the address of entry? Yep. So in that case, it would just be 9 and 10 in the buffer.
And then is there a reason why buffer length is 8? Yeah.
No. 5 would do. 5 would be just fine. So I'm just making it 8. It just over. It allocates more than what it needs.
Okay.
You can also change the tree if you want. I mean, you can always make the tree a little bit deeper and larger, so you actually end up with 8 values, and you can then see how it gets the job done.
I mean, for me, this really helped with the recursion because I'm taking the 400, so we just went over recursion literally like last week. So this
In 400?
Yeah.
You kidding me? Ah.
Yeah.
Okay. Yep. Well, this is helpful because when you get to 430, you get to do a lot more recursion. So once you have an X-ray vision of what is actually happening on the stack and how local variables are quote-unquote local to each invocation, that really helps to understand recursive algorithms later on.
It definitely helped with my understanding of pointers too, because it's like I can code away and make my program work with pointers, but it was still kind of like fuzzy what they're actually pointing to. But
Yep, and the mechanism.
Yeah, you and me both. But yeah.
All right.
This was really helpful though. I feel
Well, excellent. Well, that's the purpose of the lecture. I think it's really helpful myself, to be doing this in person instead of doing this online, through Zoom.
absolutely.
I mean, if I do this through Zoom, the gesture that I did would not convey, right?
Right.
This is where the stack pointer is. This part is in use. And this part is not in use. That would be completely lost in Zoom if it's just in my face, right?
Yeah. That's true.
And also, I think generally speaking, when it's in person, it's easier to focus because I'm the shiny object, right?
Right.
So it's easier to have something to focus on. If it's zoomed, I mean, yes, I can pop up my webcam, but after like 2 minutes, people go like, "Oh, that's just a static image.
Yeah.
Okay, I'm just gonna go shop in Amazon
For
and
my-
plan my trip to Yellowstone National Park because Tag mentioned something about."
For me, I would legit just have League of Legends in the background, and I was just like, "Oh, what am I doing?" But I can't stop. But now it's good to be in person. But
Yep.
I think I have enough to study off for sure after this lecture. I think
I
I
have-
have like a good.
I have final exam office hours, so that should be posted somewhere, and so you're
Oh, okay.
welcome to use that office hour too.
Is it gonna be like next week or just this week?
So the weird thing is tomorrow is the end of instruction.
Uh-huh.
So Friday is technically the beginning of the finals week.
Okay.
So on Friday, if you want to talk to me, send me an email first because I think I just double booked my office hour with something else. But
Okay.
send an email to me and I can Zoom too. So with Zoom, I don't have to be here.
Oh, that's
Yeah.
awesome.
Yeah.
I took Friday off of work, so yeah, I think I will Zoom.
Okay.
Because I'm going to be out of town. I'm going to Disneyland for my birthday, which is Friday.
Oh, okay.
Yeah.
Well, happy birthday.
Thank you. Appreciate it.
Alrighty.
All right, I'll message you. I'll email you if I have if I need that Zoom link so I can ask some questions.
Okay.
All right.
Sounds
Thank
good.
you, Professor.
Mm-hmm.